Okay guys, question 1. The diagram shows two pulley wheels of equal size connected by a drive belt. The radius of each wheel is 7 centimeters and the distance between the centers is 28. Calculate the length of the belt. So guys, what I'm going to do first and foremost, I'm going to draw the diameter going directly downwards. What I can now say is that this green line here, representing the belt, and this green part here, they are both worth 28 each, because they're the same as the distance between the centers. Now, if I have a red part here representing a semicircle, this red part here representing another semicircle. Okay? The length of a full circle is L equals 2 pi r. If I want to get half of that for a semicircle, what would it be? What's a half 2 pi r? Just pi r. But when I add both semicircles together, what do I get? The length of a circle. So I can just work with the length of the circle here. So what I'm going to get is 28 plus 28 plus 2 pi r, which is going to be 2 multiplied by pi multiplied by 7, which is 14 pi. So it's going to be 56, which is your 2 28ths, plus 14 pi. And then, answer there is going to be 99.98, round off to the nearest whole number, which is going to be 100 centimeters. Happy enough with that? Moving on. Part B. Okay. Diagram shows a solid cylinder of diameter 54. This means the radius is 27 and of height 70. A cone inside with the same diameter and height as the cylinder is cut from inside the cylinder. Calculate the volume of the cylinder. Volume of a cylinder is pi r squared h. Therefore it's going to be pi times 27 squared times a height of 70. So put that into the calculator. Pi 27 squared bracket 70. We get there is 51,030 pi. Are you happy with that? 51,030 pi. Calculate the volume of a cone. What's the volume of a cone? Anybody? A third pi r squared h. It's a cone, not a cylinder, okay, so it's smaller. And what we're going to get here is a third pi times 27 squared times 70. It's basically a third of my previous answer, isn't it? So just divide the last answer by 3. And we get 17,010 pi. Now, what fraction of the cylinder remains after the cone is removed? The fraction is the original volume. The original volume. And what fact remains? Volume remaining. Now guys, what's the volume remaining? Can anybody tell me? 51,030 minus 17,010 pi. So 51,030 pi minus the previous answer 34,020 pi. 34,020 pi divided by 51,030 pi. So divide this answer by 51,030 pi. 2 over 3. 2/3 remains. Happy enough with that? Yeah. Any questions? Next part. What we have here is the diagram, not the scale, represents a shot put zone in an athletic stadium. The area of CDE is a quarter of the area of the disc of centre C and radius 100. Calculate the area correct to 2 decimal places, okay? Now, this represents a quarter of a circle. There is a formula in your book though. And it says theta divided by 360 multiplied by pi r squared. What does theta represent, guys? represents the angle. What's the angle of a quarter of a circle? What's the angle of a quarter of a circle? 90 degrees. And what's 90 over 360? 90 over 360? It's a quarter. So that's a quarter of a circle multiplied by the area of a circle. What's the area of this circle? Pi times 100 squared. So 100 squared multiplied by pi equals 10,000 pi. Divide that by 4. We're going to get 25,000 pi, or sorry, 2,500 pi. And when we press the change button for calculator, we get 7853.98 meters squared. The shot put zone consists of a thrown zone and a landing zone. The thrown zone is shaded, okay, and it's the centre of a circle of radius 1. Calculate the area of the thrown zone, correct 2 decimal places. It's the answer of part 1, which is the full thing minus this part in here. So how do you get this part in here? It's a quarter of a circle of radius 1. A quarter pi r squared, which is going to be a quarter pi times 1 squared. So it's going to be a quarter of pi divided by 4. And what we get here is 0.79. 0.79 meters squared. Part 3. Oh, sorry. Calculate the area of the thrown zone, correcting to 2 decimal places. Oh, sorry guys. Excuse me, I made a mistake there. The thrown zone is actually the full circle. Yeah, not the quarter of a circle. So if I just multiply this answer by 4, excuse me, the actual answer is 3.14. So guys, the actual answer is 3.14 meters squared, because it's talking about the full circle, not just the quarter of it that's in the zone. Okay, now for this part here, I got ahead of myself. Now this part here, I'm going to need a quarter of it, which is 0.79. So 0.79 meters squared. Calculate the total area of the shot put zone. The shot put zone being the zone outside, it's the green zone here, so to speak, the zone outside the thrown part. So it's the answer of part 1, which is 7853.98 minus 0.79. What do we get here? 7853.19. Who got that? Okay, well done. Meters squared. Moving on. The colour of 500 cars that pass a particular set of traffic lights during a 2-hour period is recorded by a group of students. Okay, 500 cars in total, correct? Yes, Oscar? Sorry guys, just quick adjustment on the last question, okay? The last question, what we're doing with this blue region here is we actually found out what the green region was, okay? And the green region is this much here. And what we have to do with the green region is then add on, is that correct? Add on 3.14, because it's the full region of the circle and the grass region, okay? And what that will get us there is plus 3.14. Now that gets 7856.33 meters cubed, meters squared. Okay. Now that fits that, alright. What we're on here is 500. Okay. Calculate the number of black cars and write it into the table. It's going to be 500 minus 70 minus 100 minus 45 minus 55 minus 140 minus 140. What's the answer to that? 90. Sorry? 90. Okay. Calculate 90. Calculate the relative frequency for each one and write it into the tables, okay? So, 90, we're going to have to do each one divided by 500, and I need you to tell me what the answers are, okay? 100 divided by 500, 45 divided by 500, what else is it? 55 divided by 500, it's going to be 90 divided by 500, and finally 140 divided by 500, and then 500 divided by 500. So, what's the answer to the first one? 0.14. 0.14, next one? 0.2 after that?
0.09.
0.09 after that?
0.11.
0.11.
0.18.
0.8. 18.
28.
And when you add them all together, you're going to get 1.0. Okay, what's part C then? Suggest a method to check your relative frequency calculation is correct. Perform this check. Method. Adds all relative frequencies together. And you should get 1.0. How do you check this, guys? You write them all down and add them together. So will you call out those numbers for me again, Jack? 0.14.
0.14.
Yeah.
0.2.
Yeah.
0.09.
Yeah.
0.11.
Yeah.
0.18.
Yeah.
0.28.
Yeah. And when you add them all together, you get 1. Okay. What's the probability? Now, I want to explain what relative frequency is, guys. Relative frequency is basically, it's red 14% of the time. Oh, sorry, a red car goes through 14% of the time. A blue car goes through 20% of the time. A black car goes through 18% of the time. Do you understand? It's a fraction, 18 out of 100. So the probability of a red car is what? 14 out of? What's probably next car to pass the lights is red? 0.14 or 14%. Use the information to estimate the frequency of each colour if 2,400 cars pass through the lights in a full day. Write this information on the table. Okay, 2,400 multiplied by 0.14 for red. You multiply 2,400 by each number in the relative frequency. Do you understand why? Because 2,400 cars, out of the 2,400 cars, 14% or 0.14 should be red. 20% of them should be blue. So, can anybody tell me what the first one is?
336.
336. Next one? 4. 80 after that?
216.
216 after that?
And then 264.
Yeah, after that?
And 432.
432 after that?
And 672.
6?
72.
72. What's the total?
2,400.
And how would you check if you're right? You could add them all together and make sure that they're 2,400. Okay, guys. Moving on. And part F. The data collected by the students is not a random sample of cars passing throughout the day. The data collected by students is not a random sample of cars passing through the day. Do you think this makes your estimate in E above unreliable? Give a reason for your answer. Alright, guys, so in this question, okay, what we have is a set of traffic lights, okay, and the set of traffic lights being red, yellow and green, okay. That has nothing to do with the question, just traffic lights, alright? Now, what happens is, you have a bunch of cars going through here every day, whether it be red, green, or yellow, okay? Now, the question states, in part A, it states that the colour of 500 cars that pass through a particular set of traffic lights during a 2-hour period is recorded by a group of students. That is the whole point of the experiment, is to find out what colour are the cars that go through it. The data collected by the students is not a random sample. A random sample means that it represents the number of cars on the road as a whole. Okay? So, in my opinion, it technically is a random sample, because the number of cars that go through that traffic lights, the number of cars that go through that traffic lights most days is influenced by the people who live there every day, okay? But it is a random sample of how many different colours are on the road, okay? Passing through today, does this make your estimates they're not unreliable, so no, they are not unreliable. As they do represent the colours and frequencies of cars going through the lights.